Understanding how to train neural networks to capture word contexts is fundamental to harnessing the power of embeddings like Word2Vec. The core intuition behind Word2Vec is simple yet profound. Predict a word from its context. In this video, we'll delve into how Word2Vec learns this relationship by utilizing neural networks, exploring both the architecture and the algorithms used in the training process. So far, we've discussed the significance of word embeddings in natural language processing and implemented Word2Vec models using Gensim, particularly focusing on the skipgram technique. We've seen how these embeddings capture semantic relationships and used cosine similarity to analyze the relationships between king, queen, prince, and princess. Now, it's important to recognize the limitations of traditional embeddings, especially regarding polysemous words or words that have multiple meanings. This leads us to contextual embeddings, a new approach introduced through the BERT model. Next, we'll explore advanced applications of these embeddings in building AI agents tailored for specific tasks, sharpening our understanding of how these models adapt and respond. Now, let's set up our environment by installing the Gensim library, which is essential for working with Word2Vec. To do this, we're going to use a straightforward command in Jupyter Notebook, ensuring Gensim is ready for our project. Once that's done, we'll move on to preparing a sample dataset that illustrates how our model learns to predict words based on their context. So, we'll create a list of sentences. Each one will be a sublist of words. This structure helps the Word2Vec model learn the relationships between words effectively. After that, we'll train the Word2Vec model using the skipgram technique. When doing this, we need to specify some key parameters. The vector size is important. It defines the dimensionality of our word vectors and captures nuanced semantics. Then there's the window parameter, which determines how much context we look at around each target word. By using the min count parameter, we can filter out those infrequent words. And by setting the SG parameter to 1, we tell the model to use the skipgram architecture, perfect for our dataset size. Finally, we'll retrieve the vector for the word bank and discover other terms that are semantically similar, showcasing how effectively our model understands and represents contextual relationships. Now, let's implement the code to train our Word2Vec model using the skipgram technique. We'll be using the Word2Vec class from Gensim, which gives us the flexibility to set essential parameters like vector size, window, min count, and SG. Here, we'll set vector size to 100. This determines the dimensionality of our word vectors. Keep in mind that larger sizes can capture more nuances, but they might risk overfitting, especially with smaller datasets. Now, the window parameter gets a value of 5, which means we'll look at 5 words before and after our target word to grasp its context. This is really crucial for understanding word meanings. The min count is set to 1, ensuring that even words that show up just once are included in our training. This way, we're capturing all the nuances in our sample dataset. And by specifying SG equals 1, we're clearly telling the model to use the skipgram architecture. Next up, let's retrieve the vector for the word bank and discover words that are contextually similar. To get this specific vector, we'll use model.wv bank. And for identifying other similar words, we'll use model.wv.similarByWord bank. This function identifies other words based on cosine similarity, showcasing how our model understands contextual relationships within the dataset. This powerful functionality really highlights the core strengths of Word2Vec in semantic search. Now, let's dive into how we can implement TSNE to visualize our trained word embeddings. The first step is importing the necessary libraries. We'll need TSNE from the sklearn.manifold module along with matplotlib.pylot for our plotting needs. Once we have those set up, we'll create a list of all the words from our model's vocabulary by using model.wv.keys-to-index.keys. And then it's easy to retrieve their corresponding vectors simply by indexing into model.wv. Next, we'll apply TSNE to reduce the dimensionality of our word vectors from a high-dimensional space down to 2 dimensions. This is done by initializing the TSNE object with n components equals 2 and fitting it to our word vectors with the fit transform method. Okay, so now we have our reduced vectors ready. Let's set up the plot using matplotlib. We'll create a scatter plot to display these vectors. Each point in the plot represents a word in our embedding space. To improve clarity, let's annotate these points with their corresponding words, which allows us to easily identify their locations in the plot. Lastly, we'll add a title to enhance our visualization and execute plt.show to render the graph. This visualization really provides insight into how the words cluster together based on their semantic relationships, which were established during training. The figure shows per-epoch training dynamics across 20 epochs, and we've got 2 stacked subplots to analyze. In the top plot, you'll notice training accuracy, marked with blue circles, and validation accuracy, which are shown with orange circles, both over epochs 1 through 20. Then, in the bottom plot, we see training loss with green X markers and validation loss, depicted with red X markers across the same epochs. Now, all of these metrics are plotted on axes scaled from 0 to 1, with each epoch clearly ticked on the x-axis, plus legends to identify each curve. So, what can we glean from this? Well, a key pattern here is that training accuracy tends to be both higher and smoother compared to validation accuracy. This suggests that the model is consistently improving its fit to the training data. However, you'll notice that validation accuracy is more variable as we go through the epochs and often lags behind the training accuracy. That's what we call a generalization gap. Now, when we look at training loss, it shows a clear downward trend throughout the epochs, whereas the validation loss is consistently higher and more erratic. It sometimes even goes up while training loss goes down. This combination, training accuracy rising alongside training loss falling, with validation accuracy lagging and its loss being higher and noisier, indicates that while the model is learning some useful patterns, it might be starting to overfit as we progress through epochs. So, from this display, we can conclude that while the model is making strides towards its training objective, we definitely need to keep an eye on the validation behavior. This could involve methods like early stopping, regularization, or adjusting hyperparameters to ensure that the model generalizes better to unseen data. Let's dive into how we can implement the core training process for our word-to-vec model. We'll kick things off by defining a function named trainWord2Vec. This function takes sentences as input and goes through each word to predict the context words surrounding it. Inside this function, for each word, we use another function called getContext to pull up its neighboring context words. This is crucial because it helps the model grasp the relationship between our target word and the context it's in. Next, we leverage the model to make predictions based on the word we're currently looking at through the predict method. The prediction gets compared to the actual context words using the calculate loss function, which computes the error between what we predicted and the real outcome. This loss indicates just how well our model is doing, kind of like a report card. Finally, we call the update weights function with the calculated loss. This encapsulates the back propagation process, adjusting the model's weights to learn from its errors, aiming to improve future predictions. By iterating over every single word in each sentence, this training function effectively teaches our model to capture those subtle contextual nuances, ensuring it can accurately predict words based on their surroundings. And that's how we train our word-to-vec model. Now, deep breath in. Let's implement the following code to adapt our trained word embeddings for a sentiment analysis task using a logistic regression model. First, we need to prepare our dataset, which consists of sentence embeddings that represent the average vector of words in those sentences. Alongside these embeddings, we also have corresponding labels that indicate whether each sentiment in our dataset is positive or negative. Next, we will split our dataset into training and testing subsets using the train-test-split function. This is crucial because it allows us to evaluate our model's performance on unseen data, ensuring that it generalizes well beyond the training set. Following the data preparation, we will train a logistic regression classifier, which is a straightforward yet effective model for binary classification tasks. We use the .fit method to train the classifier on our training data. After training, we can assess the model's accuracy using the .score method on our test dataset. This will give us a quantitative measure of how well our adapted embeddings can predict sentiment, culminating in the output of the accuracy. This integration really demonstrates how powerful embeddings can be utilized in practical applications, showcasing their versatility across various NLP tasks. As we wrap up our exploration of training neural networks for word contexts, it's important to remember the many implications these models have for advancing AI technologies. You see, the ability to predict a word based on its context, it really does revolutionize how machines understand language. And this could lead us to smarter personal assistants, chatbots, or any system that relies on natural language understanding. Throughout this lesson, we've navigated the intricate process of embedding training, how this ties into neural networks, and we've also explored some practical applications that could help us foster new AI capabilities. Moving forward, we'll dive into more advanced methodologies, like adapting these models for tasks in real-world scenarios. Exciting stuff, right? Thank you for joining me on this deep dive into the world of neural networks and word contexts. Just keep in mind that language processing is an evolving field, and your ability to engage with these tools will really set the stage for building those innovative AI solutions. Happy coding!